Welcome all for this short discussion on MOS transistors. The transistor is going to be acting as a switch in digital circuits. An on transistor passes finite amount of current, and this amount of current is going to be determined by the region in which the device is going to operate. The transistor gate, source, drain all have capacitance, and this is nothing but I is equal to C into dV by dt. If I want to find dt is C by I into del V. So this dt says the speed of the device, dt is equal to C by I, and this C is nothing but capacitance, I is nothing but current. So if you want to describe the performance of any circuit, then you have to check the speed of the circuit. So this equation helps in understanding the performance of the circuit. So the capacitance and current determine the speed of the device. That is what is the upshot of this equation. And if you want to represent MOS transistor, this is nothing but NMOS, this is gate, this is drain, this is source. If we want to include fourth terminal, the fourth terminal is going to act as bulk, or you can call it this as substrate. Again, this is going to be your gate, this is going to be your drain, and this is going to be your source. And for similarly for PMOS, this is going to be your gate, this is going to be your source, and this is going to be your drain. Gate, source, and this is drain, and this arrow pointing outward represent it as a PMOS device, and this is going to be your bulk. The terminal voltage is going to describe whether it is going to operate in cutoff region or linear region, or it could be saturation. So the mode of operation depends upon VG, VD and VS. The VGS says it is VG minus VS, and VGD is VG minus VD, and VDS is VD minus VS. So source and drain are symmetrical diffusion terminals. It says that you can use source as a drain or drain as a source because both are same diffusion. So it could be used as one terminal can be either could be used as source or drain. So you should not you doesn't have to follow this should be source and that should be drain. Both are symmetrical in the sense both are made out of same diffusion. So you can use it as a drain or source. So by convention, source is the terminal at low voltage. So when the if you take any MOSFETs, the terminal which is operating at low is going to act as a source terminal. Hence VDS is greater or equal to 0. So it says what? VD minus VS. So VD is higher potential and VS is the lower potential. And the NMOS is body is ground. NMOS body is ground. So you know that what is CMOS? CMOS is nothing but it comprises of both PMOS and NMOS. So this is the base material called substrate. I am going to take P substrate. This is N plus diffusion. This is also N plus diffusion. And again, if I want to, I said it is an CMOS. So the IC chip will contain both PMOS and NMOS. We will take this color to represent P plus, and this is P plus, which is going to be present inside N well. This is my gate, this is my source, and this is my drain, and this is what is my gate, source and drain. So this P substrate is normally you should reverse bias there is a, if you take the MOS structure, there is a diode between N plus source and N plus drain with the bulk. So this diodes should be reverse bias, so P side should be connected to most negative potential, and I assume that ground is going to be the most negative potential, and I make a ground for proper operation. So that is what has been represented here. The NMOS body is grounded, and first assume source is to be 0. You make source to be equal to ground. Right? Okay. You have three regions of operation: cutoff region, linear region, and saturation. So in cutoff region, my IDS will be equal to 0. Why? Because my VGS is less than VT. Less than VT in the sense it could be negative. So device will be in off state. Current or what is threshold voltage? Threshold voltage is the minimum voltage that has to be applied to create channel between source and drain. If that voltage is negative, there will be no channel created. If there is no channel, current conduction is 0. So IDS is 0. If you go for linear region, I could write VGS greater than VTN, threshold voltage of N device, and the other condition is VDS should be less than or equal to VGS minus VTN. The other way I could represent this as VGD greater than VTN. What is the meaning of VGD? It is the voltage difference between gate and drain. If the voltage difference between gate and drain is differ by VTN, then the device is going to operate in linear region. It says that my gate potential is greater than drain potential by a threshold voltage, then the device is going to operate in linear region. That is what is being represented in this diagram: VGS, VGD and VDS, the potential difference between drain and source. If I want to make the device to operate in saturation region, I should give VGD less than VTN. So my gate voltage is going to be lesser than drain voltage by a threshold voltage, so that my device is going to operate in saturation. So the overall summary is this, and this is the first order. First order in the sense we have biased the transistor to act in various region, and we call this as first order. And the name of the person is Shockley. We have included that. And if IDS is 0, my VGS is less than VT, and the device is going to operate in cutoff region. If it is going to operate in linear region, my VDS is less than VDSAT. So this VDSAT is nothing but VGS minus VTN. So what is the other way of calling this? It is called as effective voltage, or it could be called as overdrive voltage. That is called as VDSAT, saturation voltage. When it is less than, VDS is less than VDSAT, then the device is going to operate in linear region. What is beta? Beta is conduction parameter, mu and Cox, W by L, and that is what is this. In the last slide we have seen VGD is greater than VTN. This is also a proper way of describing that the device is operating in linear region. This saturation, VGD is less than VTN. So it says that my gate voltage is lesser than drain voltage by a threshold voltage, then the device is going to operate in saturation. And this is what is depicted or conveyed by the equation. We know that the MOSFET can be used as resistor when it is biased in linear region. Similarly, the capacitance, the structure, the device structure is nothing but this is metal, this is nothing but the thin layer is called oxide, and the surface or the below material is called semiconductor. So metal oxide semiconductor is the name of the device. So metal, so gate is going to act as a plate, and below gate we have a silicon dioxide layer, so it is going to act as a dielectric, below which we have a semiconductor. We are going to bias the transistor in such a way that it is going to operate in cutoff or linear or saturation. So the channel, when it is operated in saturation region, the channel will be created below the silicon dioxide layer. On the surface or the surface above or the surface below the oxide layer, we are going to create a channel. So this is going to be my channel where current conduction is going to take place. So this channel and the plate is going to act as a plate of the capacitor, and the oxide layer is going to act as a dielectric, and we are going to obtain capacitor. So any two conductor separated by an insulator will have capacitance. Gate to channel capacitor is very important. That is what we have discussed. So approximate channel as we connected to the source, which is nothing but CGS, which is COXWL. So this is the way of approximating capacitance. And when we go to non-ideal transistor behavior, which is second order effect, when you operate the device in first order or when you bias the transistor in first order, we get some of the consequences, which is going to be the second order, which is called as I field effects. When an gate voltage is increased, so in this case the first problem is mobility degradation. When I increase the gate voltage, which is nothing but the vertical field, the current IDS is going to decrease. The second case, it is called velocity saturation. Now I am going to increase the lateral field VDS. Again my IDS is going to decrease. That is what is the consequence of velocity saturation. So the charges in the channel are going to move inside the channel, and due to lateral field, when you increase the lateral field, the drain source current is decreasing, and that is called as velocity saturation, and that is causing due to decrease in velocity of the charge carriers. When you take channel length modulation effect, the channel is going to decrease in saturation region. Why? Because when I increase VDS. So when I increase VDS, what is happening is the channel is going to be pinched off more and more, and charges will be attracted. The charges moving inside the channel will be attracted to the drain terminal. So the drain current is going to decrease. So drain current is going to increase. So if you draw the characteristic, this is what is the slope which is caused due to the channel length modulation. If you take the difference between the gate voltages, the current is going to differ. Suppose for VGS1 is 1 volt and VGS2 is 2 volts. We assume that it is going to be some 1 milliampere, and here it is 2 milliampere. And if you increase the gate voltage still further to 3 volts, the current may be like 4 milliampere. So if you increase the gate voltage step by step, the current variation will not be equal at the drain side. So that is what is the problem caused by all these I field effects and channel length modulation. And if you take threshold voltage, the body effect is going to come into picture. When you stack more number of devices, the condition for a MOSFET is source to substrate voltage should be 0. It could be maintained easily for a single transistor. When you go to number of transistors, or when transistors are connected in series, we cannot be able to check whether all the source and bulk or source and substrate are sitting at the same voltage. So this is coming because of difference in potential between source and bulk. And second one is drain induced barrier leakage. When you increase the VDS, when you increase the channel length is going to decrease. Because of the decrease in channel length, VTN has to be decreased. So channel length is directly related to threshold voltage. If the channel length is larger, threshold voltage has to be large. So it is directly related to length of the channel, and this is called as drain induced barrier lowering. So when drain voltage is more, the depletion region is going to increase, and the channel is going to decrease. The channel is going to move towards the source end, and because of the decrease in channel length, automatically we have to reduce the threshold voltage, because the gate will lose its control, because we have increased drain source voltage by a large quantity. The third thing is called short channel effect, which is nothing but when we are scaling the devices to reduce the length of the device, or the reduce the feature size of the device, to miniature the device, so that large number of devices can be fabricated on the same substrate. So if that is the case, the length will be reduced. So when the length is reduced, the threshold voltage will automatically be reduced. So it is called as VTN roll off. Why? Because of scaling. Leakage, subthreshold leakage, even when gate voltage is lesser than threshold voltage, there is some leakage current which is happening inside the channel, which is due to or the relationship in the current is exponentially related current. It is happening below the threshold voltage, so it is called as a subthreshold leakage. Gate leakage, when you apply a lot of potential at the vertical field, that is vertical in the sense gate, then the charges will be swept away from the channel into the substrate, and it is going to cause tunneling, which is called as tunneling, where there are two types of tunneling: band to band tunneling, and you have direct tunneling. Junction leakage, in the sense, if in the previous slide we have seen this. So this is P plus, and this is P, this is N well. So this P material and N well is going to form diode. This is going to again form diode, and this P and this N well is going to create another diode, and this is P substrate, this is N plus, this is also N plus. So if you take this is the diode. So totally 5 parasitic diodes has been created for a chip which contain both NMOS and PMOS. So all these diodes will be reverse bias. There will be leakage when you reverse bias a diode. It is called as reverse saturation current. So when you take a processor where there will be millions of transistors, when these millions of transistors, these diodes are parasitic, and this will be normally reverse bias. The leakage current will be more in the case of a processor where billions of transistors is present in a same substrate. So this is to be considered, because for two transistor itself we are getting a leakage current from 5 reverse bias diodes. So if you take millions of transistors, the power consumption is going to be increased, because power is nothing but voltage into current. When this leakage current is more, then power consumption of the IC is going to enormous. So we have to control this. We then discuss about what is called as the pass transistor logic. I am going to consider NMOS transistor. This is source and this is drain. When gate voltage is 0, the connection between source and drain is disconnected, so there is no output. When gate is 1, source is connected to the drain. So when 0 is being connected at the input and gate voltage is 1, so we want to operate it as an on switch, so we give G is equal to 1, input is 0, output will be transferred, and it is also 0. It is called strong 1. When you give input as 1 and gate is also 1, the output is going to be degraded. In the sense, when you give gate is called control input, and I am going to give gate drain 5 volts, gate is also 5 volts. The source could go up to VDD minus VTN, so that it can operate in saturation or in cutoff region. So this is the limit it can go. So if that is the case, my 5 volt which has been given at the input or which has been given at the drain terminal is going to be reduced by VDD minus VTN. So when you cascade the connection, you will get degraded logic 1 or weak 1. So that is the logic here. And if you take PMOS, this is source, this is gate and drain, and if you give gate equal to 0, the switch is closed. When the switch is closed, when you pass 0, it is going to be degraded 0, and when the switch is closed, when you give 1, it is going to pass it as a strong 1. So NMOS, strong 0, weak 1. Weak 1 in the sense the voltage level is going to be reduced, or when you go to PMOS, it is going to be weak 0, strong 1. That is what is pass transistor logic, where transistor is considered to be acting as a switch. Next gate is called transmission gate. We are going to use the pass transistor or MOS transistor in such a way that you are going to have both PMOS and, so this is nothing but NMOS and this is nothing but PMOS. So NMOS can pass strong 0 and PMOS can pass strong, NMOS can pass strong 0, PMOS can pass strong 1. So when it is combined, you can obtain the benefit of passing strong 0 or passing 1. Under which condition? When this gate is equal to 1 and this gate is equal to 0. When this has been satisfied, the switch will be in on condition and you can pass either 0 or logic 1. That has been written here. When gate input is 1 and gate bar input is 0. So when you pass 0, it is going to send a strong 0. When you pass 1, you can pass 1 at the output as strong 1 under the condition when gate is equal to 1 and gate bar is equal to 0. And these are the various ways of representing transmission gate, right? These are the various ways, and this dot says it is negated, right? With this we will conclude this session, and thank you all. Thank you.